The fractional domain. Let Xis denote the fraction of a subset S that player I receives in allocation X. Assume that her value for that fraction is Xis times Bi of S. The welfare maximization becomes an LP. Maximize the summations of Xis times Bi of S, summing for all I and the S pair not equals to empty set. Subject to the summations of Xis, summing for all S which is not empty set, is less than equals to 1 for each player I, and subject to another constraint, doubling summation. With outer summation summing for player I, all index I, inner summation summing for all S such that J is in S. Xis is less than equals to 1 for each item J. The third constraint is the trivial constraint Xis, which is greater than equals to 0 for all I and S not equals to empty set. By constraint 12.4, a player receives at most one integral subset, and constraint 12.5 ensures that each item is not over-allocated. The empty set is excluded from technical reasons that will become clear below. This LP is solvable in time polynomial in its size by using, e.g., the ellipsoid method. Its size is related to our representation assumption. If we assume the bidding languages model, where the LP has size polynomial in the size of the bid, e.g., k-minded players, then we have a polynomial time algorithm. If we assume general valuations and a query access, this LP is solvable with a polynomial number of demand queries. See Chapter 11. Note that in either case, the number of non-zero Xis coordinates its polynomial. Since we obtain X in a polynomial time, this will become important below. In addition, since we obtain the optimal allocation, we can use VCG, see Chapter 9, to get Proposition 12.12. In the fractional case, there exists a truthful optimal mechanism with efficient computation and communication for both the bidding languages model and the query access model.